Hello everyone. Welcome to my presentation on the course project of Applied Deep Learning. The project is about detecting cancer metastasis on gigapixel pathology images. A little bit intro. The treatment decisions for more than 230,000 breast cancer patients in the US hinge on whether the cancer has metastasized away from the breast. The metastasis detection is currently performed by pathologists, which is a very labor intensive and error-prone task. The, the paper proposed a method which leverages a CNN architecture and obtains results on a chameleon 16 dataset in a challenging lesion level tumor detection task. In this project, I have tried a simpler version of the same technique proposed in it. So the available dataset of chameleon 16 consists of slides and masks, which are of TIFF files and are huge because they embed information of about 8 zoom levels. On the top right, you can see the different sizes of the different zoom levels for a particular slide with the downsample factor. On the right, you can see the overlap of the slide and the mask, and the red regions on the overlap image detects the tumor cells. So the model architecture that I have used consists of pre-trained model inception V3 with ImageNet weights. It consists of two sorts of input. The first input is the image with a zoom level of 3, and the second input consists of the zoom level 4. Both the inputs have the path size of 80 cross 80. It has a center of 50 cross 50. As there were 21 slides available, I have used the training slide 18 slides as training data and 3 slides as test data. The dense layers have 256 and 128 units respectively. The dropout is 0.2 and global average pooling 2D layer is added after the pre-trained model to flatten the output before concatenating. Let's go over the dataset creation overview. First of all the slides and masks with the zoom level of 3 were sequentially loaded into the memory, and the patch size of 80 cross 80 was created from it. There was a stride of 50, so there were few overlapping patches. And then for each of the patches, you check whether there a tissue percentage between, first of all, you find the center region of 50-50 and 50 cross 50, and then check whether any tumor cells exist in the mask. If there is a tumor cell, you save that patch and label it as 1. If no, you check the percentage of tissue cells in the patch and check whether if it's more than 50% tissue, then yes, you keep that patch with a label of 0. In this process, you keep on storing the coordinates in the previous step. You keep on storing the coordinates so that you can find the corresponding patch in the deeper zoom level. The ratio of tumor slides to normal slides was quite low, and thus random undersampling was applied to balance the dataset by reducing the number of normal slides randomly. So now the dataset finally consists of two patches of similar image of different zoom levels and its labels. I've used sklearn train test split to split the slide numbers into training and testing with a test size of 0.1, which resulted in 18 train and 3 test slides. The final dataset had 24,000 train images of 80 cross 80 size and 17,000 test images of 80 cross 80 size, and both the zoom levels were there. Let's go over the model training. First, I created a pre-processing function to apply the data augmentation and rescaling to feed the image into the model. Then the balanced dataset which was created in the previous step that was loaded into the memory using image data generator, and different generators were used for train and test. The binary cross entropy loss was used and sigmoid activation was applied at the output to get a value between 0 and 1 to create a heat map. 0 implies it's non-cancerous and 1 implies it's tumor. Then we create and fit the model with checkpointing callback for 10 epochs with a batch size of 16 and Adam optimizer with a learning rate of 0.002. On the right, you can see the graphs of training and validation accuracy and the loss with the epochs. After the model was trained, for inferencing, we applied a similar patching technique. All the inference slides we broke down into different 80 cross 80 patches for both the zoom levels, and then gave the model as the input, and then the output, which was a value between 0 and 1, it was kept as the output for that particular patch. And then these output values were used to generate a prediction mask like heat map for the slides using the coordinates in the patches. On the below, you can see an actual overlap with the predicted mask overlap on the right. After the creation of the predicted mask, the evaluation technique used was ROC. The receiver operating curve was used to find the FPR and TPR along with the threshold. The area under the curve was calculated, and based on the true positive rate and false positive rate, the optimal threshold was calculated. The optimal threshold is the point where there is a maximum difference between the TPR and FPR. Then sensitivity and specificity were calculated at the optimal threshold. And then using the optimal threshold, we calculated the precision and recall for the mask. Here are the results. So you can see this is the actual in the middle, you can see the actual overlap between the mask and the tumor mask and the slide. And on the right, you can see the predicted mask and the slide. Uh, Here you can see that the sensitivity and specificity along with the recall is higher. The precision is a bit lower. The optimal threshold found was 0.5. Again, similarly, here our precision is also higher along with the recall and specificity and sensitivity. This again, we can see that the precision is quite low, but the recall is good. The sensitivity and specificity are good enough. The optimal threshold found was 0.023. Here is another result. Here again, we found an actual patch and a predicted patch, and the recall is still quite high, which is good for our model. In this particular one, we can see that the actual has a very small size patch in the center, and a little bit red was predicted, which is good. So our recall is a bit lower here, and the sensitivity and specificity are good enough. Here is again an actual and a predicted patch, which looks quite similar. Our precision here is 0.5 and the recall is 0.98. The optimal threshold found was 0.21. So for the conclusion, I have used magnification level 3 and 4 with a patch size of 80 cross 80 due to collab RAM limit. The model trained has high recall and variable precision, which means it can classify actual cancerous cells effectively, which is essential in our case. Using a pre-trained Inception V3 model with the ImageNet weights and freezing the first half of the layers resulted in starting with a higher initial accuracy and required less data for fine-tuning. Sensitivity and specificity are higher at the optimal threshold, which means that the model can correctly identify patients with and without the disease. Let's go over the code. So for the dataset creation, we have installing required libraries, adding the required inputs, and here are a few helper codes which were already provided, which it consists of reading the slide, finding tissue pixel and get tissue percentage, and then applying the mask. Let's go over the dataset creation code. First of all, the patch extraction was done. We read the slide and the tumor mask, and then create patches for the slide, and then go over each of them sequentially. We find the center of the particular patch, and then check if there is any tumor cells within it or not. If there is, we directly add it to our tiles and label the uh, patch as 1. Then we continue if we are done with it, if it was a cancerous one, or else we find a patch and then then we calculate the percentage of tissue. We only keep the patch which has more than 50% of tissue. Then we delete the images which we opened to free up the RAM. And then for random undersampling to balance the ones and zeros, we randomly shuffle the data and keep the minimum length of like whichever the tumor cells and the non-tumor cells. If we keep the minimum length and just keep the first half based on the shuffled tumor and normal IDs. And then we find one level deeper image and then read the slide. And based on the found coordinates in the previous part, we find the zoomed out version of that particular center, which we will see below. Then we mount the drive and just get all the data and then get only the slides with corresponding masks available. Then divide the slides between train and test. For the training part, we define a level of 3 and then we find the tiles, indicators, and zoomed in patches by extracting it. So here you can see the processing code. Then After processing each of these tiles, we save them in NumPy format as they all are arrays, ND arrays. Then we load the data from the stored patches, and then we distinguish between the positive and negative samples and store them separately, positives and negatives. Here is a sanity check to find the zoomed in and zoomed out patches with the same center. So on the left, you can see a zoomed in patch and the zoomed out version of the same patch on the right. Both are 80 cross 80 pixels. So these are few examples where you can see the left is zoomed in and the right is zoomed out. Similar process is followed for the testing patch. And then after this, all the train and test patches are stored in the drive based on this directory structure with train, positive, drive 3. It's based on the zoom level. Zoom has a train and test, which has pause and negative. So this is how we are creating our data set. So after the data set creation, let's move on to the model training. We first mount the drive to get the data, and then sanity check whether all the slides are there or not, install the required libraries, add all the imports, and then for the data set, we load all the NumPy files which were saved based on the positive and negative value, and then concatenate them to get the train and test patches for Zoom 1, Zoom 2, and the indicators. Here is just a sanity check to find the number of examples that we have, that is 24,000 and 17,000. Then we apply data augmentation and rescale function as it's defined in the paper. We rotate the image by 90, then we flip it left and right. Then we apply random brightness, saturation, hue, contrast, and at the end rescale it to -1 and 1. After this, the image data generator is created, and then we define our model. So first of all, there is an inception v3 pre-trained with the image net width. Then we freeze the first 150 layers, and then apply sequential model where we add the inception model and a global average pooling model. And then we define the input as 8083, and this is the encoded output 1. Similarly, we do it for the zoom 2. And then here we add a dense layer, a dropout, again a dense layer, and the output layer with a sigmoid activation. So here you can see the model summary. This is the model that is created, which has 2 inputs. Then we train the model. First, we create a checkpoints directory, and then we load the model from the checkpoints if it exists, and then we compile and fit the model, and then plot the results of training and validation accuracy and loss with the epochs. So now the last part which comes is model inferencing. So these are the same helper codes which are provided to us, finding tissue pixels, reading slides, tissue percentages. And here is the code to predict the tumor. We read in the slides, we read in the mask, we read in the slides for 2 zoom levels, we read in the mask, we create patches. And for each patch, if it is the tissue percentage is less than 50, we just append 0, or else we apply model predict on it. And as we apply model predict, it gives you a value between 0 and 1, which helps you to create a heat mask. And this is the mask that is created. We initialize the mask with all the zeros, and based on the predictions, we find the center, and then we apply that mask prediction for that center with the predicted value, which is just found. So this is the code to plot the results, and this is the code to evaluate the prediction mask. So for evaluation, what we are doing is we are finding the ROC curve, which gives you the FPR and TPR along with the thresholds. We find the AUC, and then we display the ROC curve. Then we find the optimal threshold index by finding the argument maximum of TPR minus FPR, as discussed before in the presentation. We find the optimal threshold, print out the AUC, specificity and sensitivity at that particular index are also printed out. And then we find the precision and recall based on that optimal threshold. So let's go over the example on trained data set. So this is the tumor 91 for which we have trained the model. And on the left, you can see what's the actual patch, actual slide and the mask. And on the right, you can see the predicted mask and the slide. The optimal threshold AUC and precision, you can find it here. The recall is quite high, as discussed. This is again an example of 110, where you can see the tumor cells on the left and the right. This is the predicted one. Here, the precision is quite high as well. And this is the ROC curve. Then for the test data set, let's look at an example. This is 75. So on the test data set, we are able to identify these regions as well. So the recall is higher, but the precision is quite low. That is okay with us. So this is the last example of the second test, which is slide 84. And here we can see the red region, and this is the predicted mask. And this is the output for the same. So that's it. Thank you.